Welcome. Thank you for your participation. Today I'll talk about my thesis on reproducibility of graph neural nets in multiview brain connectivity. Here's our agenda. We'll first start by network neuroscience. We'll give some definitions here about brain scales, neuroimaging, and brain connectivity. And then we'll continue with our introduction. We'll talk about here some of the major problems in network neuroscience and our aim in this thesis. And then move on to the mathematical model, the theory behind neural networks used in our thesis, and some explanations. And then we'll talk about a little bit of literature review. What are the previous methods? What is the state of the art? And the critique of the state-of-the-art method. And then we'll propose our solution, quantifying reproducibility, what is our problem and what our proposed method is. And then for validation, I'll talk about numerical experiments, and I will discuss our findings, and then for final remarks, we'll conclude it. Understanding the brain actually is vital because it helps us comprehend human thoughts and actions, paving the way for progress in health and neuroscience. To do so, we use brain networks. Brain networks actually are a conceptual model. It's not a physical thing that represents interconnected neural pathways in the brain. They reveal how different brain regions communicate and providing insights, the root of neurological disorders. The ways that different parts of the brain communication and interconnected brain regions are called brain connectivity. This is what we use to create such networks. These ways can be either physical connections or information exchange. There are different parts of brain regions. If they are physiologically interconnected, we call this physical connections. Or, for example, if I raise my hands, some of the neurons fire up my brain and then comes back to the axons in my arm. So some of the brain regions are fired up. And if these are connections, for an information exchange, we call it a functional connectivity. So, as I said, if it's a physical connection between brain regions, we call it structural connectivity. Whereas if it's a pattern of neural activity that occurs simultaneously in different areas, we call it functional connectivity. We'll get to that to explain some of the neuroimaging techniques in the upcoming slides. And here we have another term that we're going to refer in the also upcoming slides for defining our problem. Each representation of the connections in the brain by different structural characteristics is called view in a multigraph datasets. These characteristics, there might be different characteristics. We are going to give some of the examples to that. For example, it might be some of the surface of a specific brain regions or the line that separates some of the brain regions. How long is that? There are some, we can say that it's basically a feature that gives specific details about the brain regions. Network neuroscience field consists of various sub-areas such as neuroscience, neuroimaging, model analyzing, and graph theory. In terms of our thesis highlights, we'll touch upon a little bit of neuroimaging and model analyzing. Let's summarize neuroimaging first. It's a field that involves various techniques for visualizing and examining the structure and function of the brain. We categorize neuroimaging techniques as functional and structural neuroimaging. We obtain structural connections, structural connectivity that we just mentioned, using structural neuroimaging techniques, whereas for functional connections, these are captured by functional imaging techniques. The data set that are used in our thesis is created from T1 weighted magnetic resonance imaging. It's basically a structural neuroimaging technique, and this gives us some clue about how we are going to perceive our brain regions in our thesis. We can summarize T1 weighted magnetic resonance imaging as a neuroimaging technique that emphasizes the contrast in the tissues based on their T1 relaxation times. Let's talk a little bit about the model analyzing too. We can categorize analyze methods for brain networks as manual and machine learning based. The first uses graph theory concepts heavily and require a lot of handcrafted feature engineering manually, whereas machine learning based techniques are in a more automatic manner because of its interesting characteristics. Brain has intrinsically complex structure, leading machine learning based techniques to be used more frequently. Leveraging neural networks, particularly for their automatic feature extraction and large-scale data processing, has made deciphering complex patterns in the brain networks more accessible. So we talk about this, and we can categorize these network neuroscience problems that are solved using graph neural networks as the integration of brain graphs, the prediction of brain graphs, and classification of brain graphs. So before narrowing down to our thesis, first I'd like to broaden the problems that are used in graph neural networks, and then we'll just narrow it down so that we can talk about, especially in our thesis, in terms of our thesis. The first problem is the integration of brain graphs. This problem deals with creating a unified and meaningful representation of a brain population. We have brain networks from different patients that belong to a specific brain state, such as, say, autism, normal control, schizophrenia, etc. We use these samples to generate a unified and meaningful representation of a brain population that contains common and shared characteristics of the brain state. So after feeding into these brain networks, we obtain a final brain network that contains shared and specific characteristics of a specific brain state. So it gives us some clues. They can be used, some discoveries, and so on. To do so, in this very problem, we first turn our brain data into graph format and adjacency metrics. We then train a GNN model with our training set. And in terms of this problem, we can think of this model as an encoder-decoder architecture that takes all these different samples and generated the shared characteristics of a brain state in the same size. And we call it a CBT, a mapped adjacency matrix of the same size that is unified and meaningful representation of the brain state. It's basically a compressed version of the whole population that we fed into our model. To optimize this CBT, we use our validation set and employ a loss function that minimizes the difference between the generated CBT and each sample in the validation set using a distance function in an unsupervised manner. Because we don't know what are the shared and unified characteristics of a whole population, we just take a subset as our validation set and compare our final output with each of the brain sample in our validation set. Based on the difference, backpropagation mechanism of the model comes into play and updates the weights of the model so that it can generate better and better unified and generated CBT, so that it can capture the maximum characteristics of the whole population. Another problem is the prediction of brain graphs. This problem deals with synthesizing brain graphs from specific samples in a dataset. Medical imaging is expensive and inaccessible at some point. Thus, one of the biggest obstacles to achieving good results is the inadequacy of the dataset. This will help solving problems such as overfitting that may occur due to small data, as well as contributing to have generalizable models by creating large data sets, because in this way, the model covers the sample space better. The primary goal, as we said, is to predict a target brain graph based on a single source graph. To do so, a generative-based GNNs are employed. Other than an encoder-decoder architecture, as in the previous problem, here the model that is used, actually, it's a generative model. We can say as a GAN-based model. And in this problem, other than creating large data sets by synthesizing brain graphs, we have some sub-problems too, such as generating a high-resolution brain graphs or predicting the state of a brain graph at time t. For example, in order to inference how it looked like a specific brain graph in 6 months during a crucial disease, let's say. Those are also proposed in the literature. The last problem we mentioned is the brain graph classification problem. It's also the problem that we're going to work on in our thesis. This is an important problem for solid reasons, say an early disease diagnosis, for example, especially such as Alzheimer's, autism spectrum disorder, etc. There are two main problems here. One is to classify brain graphs according to whether they are healthy or not. It's simply a simple classification problem. And another is to determine the discriminative features in an unhealthy brain graphs. This can provide insights into the origin of the existing disease. And it also gives our model a flexible way, because it also gives some interpretability to the model. This is especially important in terms of clinical relevance, because in medical applications, this is what doctors are checking. However, all of these problems, the three problems that we just mentioned, share a prime challenge. They only maximize their success metrics, such as accuracy or F1 score, or minimizing their distance score, as in the first problem that we just said. They miss how their results are generalizable and reproducible in a different data distribution, or what biomarkers might cause a disease. For example, questions such as if a model is based on a noise learned during training, or if it really relies on a feature related to the solved task, are essential considerations. These factors are as critical as optimizing the targeted metric, because determining if the obtained score truly represents the entire problem and data space is a significant challenge. Okay, we have some good accuracy or F1 score, but is it really what we have? When we have different data distribution, would we still have the same scores? Or say we have some good results, but are we really sure that if these good results are related to the features that is specific to our problems? These are important problems, especially for determining for our successful for our metrics that we try to achieve. We talked lots of things about graph neural networks and the network neuroscience problems that we solved using neural networks, but we really didn't talk about graph neural networks. I'll talk a little bit about it too. As you know, graph data structures that consist of nodes and edges help flow the information. And graph neural networks basically are neural networks designed to process graph structure data. It captures semantic relationships between nodes. Here we use graphs as adjacency metrics, and you can think of okay, we have an adjacency matrix. We can think of them as images and fed into a convolutional neural networks. But when we have convolution, normal convolution that process images in an Euclidean space, they don't capture semantic relationship between nodes. And that is what we have graphs in the first place. So here in graph neural networks, those convolutions are designed in a way that captures all this semantic relationship between nodes. Three fundamental components we have in GNNs, and we can say them as node embeddings, message passing, and aggregation functions. Node embeddings is actually basically, as you know, the goal of, as I said, GNNs is to learn embeddings for each node in a graph, which capture both its local and global structure information. So in each specific node, we have features. And we have a GNN model that transforms these features in a way that maximizes our desired metrics. Nodes and their adjacent nodes interact to collect data about their nearby surroundings. Based on their neighbors in each level, nodes refine their representation. And we can express this is here as an equation here. Here, H is the embedding of node V at layer L, whereas N of V is the set of neighbors. And aggregation here is a function that aggregates all of these information. What is done here is basically for a specific node, its neighbors are checked and their features are taken. And then for each node, we have an aggregation function, and it combines all these semantic relationship using their neighbors and aggregate them in a way that it maximizes our desired results. Here, we can think of this node actually is all of these nodes are neighbors to each other at some point, although they have different hierarchies, for example, neighbors, neighbors to neighbors, neighbors, neighbors to neighbors, and so on. Considering this hierarchy, the graph neural networks try to get as much as the semantic relationship between all the nodes. And this is where it really, this is where the place GNN is really powerful. There are different aggregation functions. Some of one are simple, say, averaging or taking maximum of the features in a embedding, or there are much more complicated, such as graph convolutions. And this is the message passing mechanism and aggregation functions. In order to summarize all of these different parts of a graph neural networks, we can say each layer employs a message passing mechanism. And every node updates its embeddings by incorporating information from local and global nodes. The embeddings obtained at the final layer can serve different purposes, depending on the design of the last layer in the architecture. In terms of our specific classification problem, we can think of them as node classification, edge classification, or in our thesis case, graph classification. GNNs employed in this thesis are the same as in RG-select. RG-select is the state-of-the-art method that we're going to give much more details in the upcoming slides. In terms of a fair comparison, we take the GNN models as in RG-select, and we have 5 different architectures here. Those are graph neural networks architectures. Those names are diffpool, GET, GCN, SegPool, and graph unit. For GET and GCN, those are basically are not designed for a graph classification problem. We added a global mean pooling layer to each node in order to use them for graph classification. Basically, it is what is done in an RG select method. We just take it from there, as I said, in order for a fair comparison. So The primary objective of this thesis is to examine graph neural networks with a particular emphasis on reproducibility. We chose the graph classification problem from the three fundamental problems mentioned before. Models, the GNN models that we just mentioned are trained with multi-graph datasets from T1 images. They are employed to classify if a given multigraph is with autism. Basically, it's saying that if a person is autism or not. This is what we're going to try to understand from the problem. And actually, the focus of our thesis is not to classify them in a better way. As we said, we just focus on the reproducibility of this classification. And we'll try to offer a method how we can measure and assign a reproducibility score based on each of these models' reproducibility capability. We conducted all the designs and experiments for our reproducibility method on graph classification problem. And we propose a method, which we call the RepNet, that assigns a reproducibility score to each GNN. But this work with some minor tuning can be extended into other problems as well. As we just said, the last layer of the graph neural networks basically specifies what kind of problem that we're going to solve. So with some minor tuning, we can use this method to measure reproducibility of another problems and another models. So we have 4 problems. We have 4 questions that we're going to find an answer at the end of this thesis. What assumptions should a superior method rely on? Are the reproducibility scores correlated with their capability? How do GNN architectures rank? And what are the highlighted keys? And are the top biomarkers from the best model clinically meaningful? We'll move on to literature review. For a primitive works, we can say cross-validation or bootstrapping are trying to measure reproducibility at a rough level. Cross-validation divides data and trains on subsets, and bootstrapping randomly samples data from our training set, from our whole set, and trains multiple times using different data samples. These give some primitive clue about reproducibility. For example, using different trained data sets, we can see the metrics that we get are really close to each other and so on, but it is an indirect way. For example, if you choose a metric to optimize as an accuracy metric, we can see the reproducibility from the accuracy metric. We don't have a specific score or a specific metric here. Neither a reproducible score nor it is correlated with a model reproducibility capability also. We have some rough ideas, but we really are not sure if those numbers represent the model's reproducibility capability. It doesn't, because those metrics are for another purposes. Another serious work is identifying the best data-driven feature selection method. For a brain state classification problem, they apply various feature selection methods to the SVM classifiers that are trained individually. Here they define reproducibility as the shared biomarkers across different feature selection methods. Since they're trying to solve the same problem, they think that those feature selection methods will share biomarkers across different methods. They build a graph, an adjacency matrix made up of n nodes from a collection of n feature selection methods. In this adjacency matrix, each node represented an feature selection method. And each edge linking 2 nodes records their relationship by a certain feature. they're trying to here create some sort of different features across two feature selection methods. For example, accuracy similarity or stability similarity. Those are some of the metrics that they defined, or reproducibility similarity. And they try to measure if those two different feature selection methods have some characteristics. They have a function that takes these features and then output a number that gives a ratio or a similarity metric between those two feature selection methods. And they fill up these adjacency metrics. And basically here, in this way, each of the feature selection method is matched with rest of the other feature selection methods and how they are correlated. And they fill all these metrics with these numbers. And then since they employed three different matrices like this using three different functions, and then they averaged those in order to reduce these three adjacency metrics into one matrix. And then they sum up these adjacency metrics along any axis for using a graph, a node strength attribute of from a graph theory in order to see if any of the feature selection methods, which one has the much more common characteristics with the rest of the other feature selection methods, in order to see which of the feature method has the best reproducibility. So in this work, just as our multi-graph data sets, this method also works with multi-graph data. It identifies most discriminative biomarkers, and it finds the most reproducible feature selection method. However, it extracts the features in a manual way, not suitable for GNNs. The classification procedure is not end-to-end, leading even the most reproducible feature selection method cannot obtain competitive results because, as I said, we cannot train them end-to-end. Another work here, this is 1 year after, it's 2021. They still for a brain state classification problem, this time they proposed a graph topology based framework to select the most reproducible model. Here, they assume that diverse GNNs will identify overlapping top biomarkers because they try to learn by the same problem. Again, they built a graph made up of n nodes from a collection of n GN architectures. Here, for each node represents a GN architecture, and they try to extract some of the features from those graph neural networks and checks if which of the graph neural network architecture matches with rest of the graph neural network architecture features most, in order to see if which architecture has the best reproducibility. All matrices with different hyperparameters, they use different hyperparameters and generated lots of adjacency metrics of these, and they average them and then sum along an axis as in the previous study in order to have a specific score for each of the graph neural network models. Here, just as in the previous one, it works with multi-graph data. It identifies discriminative biomarkers, and here it finds the most reproducible GNN model. We just got a little bit closer to our problem, and it extracts the features automatically. However, this method only focuses on intermodal reproducibility. It doesn't consider interview reproducibility. We'll talk about these one in the upcoming slide in the state-of-the-art method. So this is our state-of-the-art method. In the upcoming slide, we'll have a diagram, and I'll sum up all of these three methods, and I believe it will be much more obvious what they're trying to do here. Here in this problem also, they proposed a graph topology-based framework to select the most reproducible GNN model, here using intermodal and interview reproducibility. They assume, again, that a model will identify overlapping top biomarkers across different GNN architectures and different views that we just defined in the previous slide, that it is trained on. Here they will build two different type of graphs made up of n nodes from a collection of n GNN architectures. And here, as in the previous ones, where each node represented the GNN architecture and each edge linking two nodes records the ratio of shared top biomarkers. View specific metrics examining similarities between biomarkers of different GNNs. The GNN specific metrics is assessing similarities between biomarkers of GNN trained with different views. So here, let me make it a little bit bigger. Yes. For this problem, we have a brain multigraph data set composed of n subjects and different brains, and we have different views. You remember, view was just a specific physical connection that connects interconnected brain regions. Those are different physical activities in the brains, and each of these is a specific data set. And we have, say, n GNN models. We trained each of these GNN models. Here, for example, in our thesis, say, we have 5 different GNN models, 5 different architectures. We trained each of these architectures using this data set, first view. And then we take the last layers in order to extract some features. They extract last layer. And for another views, we have 6 different views in this data set. They train 5 of these models in a total of 30 models, 6 times 5. And then there are 2 different adjacency metrics that they're trying to fill up. Those are called interview GNN specific metrics and the other one. Here, what they're trying to do, for example, for a view specific reproducibility matrix, it is view specific. The view is the same. We have 5 different GNN models. We take their extracted features and then check which of the top biomarkers. For example, here, say we have 35 different features from each of the models, and we take the top 10 feature biomarkers. They took 10 features from each of the models, and then they check which one of them match with each other. In these 10 top biomarkers, how many of them have been found in the both models? This ratio comes into this slot, and it is filled up here for a first GNN and the second GNN architecture. And then they created these adjacency metrics like that. And they do this for each view, and they created all these view-specific reproducibility metrics. In terms of GNN-specific reproducibility metrics, here, they use the same type of GNN architecture. For example, say, diff pool is the architecture, but it is trained with the first view. It is trained with the second view, and so on. And then, for each of these same architecture trained with different views, they extract their features, and then they took their top biomarkers, say 5 biomarkers, and then they check if how many of these biomarkers are found in each of the data sets top biomarkers, and then they put the ratios are here. And then they created for these matrices for each GNN models. And then they averaged those matrices in order to have in order to reduce the adjacency metrics, and then they sum along in any axis in order to further reduce these 5 scores into 1 for a specific model. And then they have a reproducibility model because they just checking that, okay, this first GNN model has some 3 top biomarkers here with the first GNN. 5 1 is with the second, 6 1, and then they take it and normalize it, and then they have a specific reproducibility score. This is basically the main pipeline that they're trying to measure the model's reproducibility. Lots of good things are here. Other than the previous advantages, this model also considers both intermodal and interview reproducibility, and it is the state of the art. However, we'll criticize the state-of-the-art method in 3 key areas: the definitions and hypotheses, the methodology, and experiments. Reproducibility of a model depends on the intersection of models' biomarkers with the biomarkers identified by other GNN models. This may affect the reproducibility score, especially when models with low reproducibility are involved, potentially skewing the score of highly reproducible models. We have a good reproducible model, and we have also a bad reproducible model. They don't have any reproducible capability. We're trying to, in this hypothesis that they do in RG Select, they try to find some common biomarkers here. But since the models with low reproducibility cannot obtain some of the unified features, when we try to check what are commons in this one, the first model has the features that we need, whereas the other has the features that we do not need. So this skew the scores of highly reproducible model. This hypothesis is wrong. And also, since they're trying to measure reproducibility by using other GNN models, when we have different set of GNN architectures, the score of the GNN model will change. So it's basically, we have an inability here to independently calculate a score based solely on model's capability. As I just said, the score is influenced by the reproducibility of other models. For our methodological problems, as I said, different matrices are created, and the top biomarkers, they use different top biomarkers. For example, they created a matrix for a threshold of 5 top biomarkers, 10 top biomarkers, 15 top biomarkers. The limited number of thresholds raise concerns about the reliability of the reproducibility score. Say we determined the threshold value of 10. If a biomarker is in the top 10 biomarkers, we added 1 to the denominator. You know, we will just get a ratio. However, it doesn't matter if a biomarker is in the 5th place or in the 9th place. No matter which plate it is, this feature make equal contribution to the reproducibility process, which is wrong. Since they use discrete space, we have an information loss here. And also, as I said, they have lots of different adjacency matrices, and they averaging them in order to reduce them to obtain a specific score. The averaging operation cause lots of significant losses. So for this method, we cannot really make sure if the scores that are obtained in RG Select, we cannot trust them. And for experimental issues, the method's robustness is questioned. So basically, after they used views average and rank correlation, those are interview and intermodal reproducibility scores. In order for external validation, they employed different functions here. For example, they checked their L2 distance, KL divergence, and so on. And they sort all of these models in terms of their reproducibility. And they claim that when we see all of these methods, when we do majority voting, we find a model that is compatible with our findings. For example, when we do majority voting for all these 8 methods, they found GET is the most reproducible model. And then they just used RG select and they found that GET is the most reproducible model. This is true, but it is missing an important thing. When we check the other models, for example, here we have 8 different measures, and GET has 4 first reproducible model ranking. In all of these models, GET out of 8, GET has been in the first place with the 4 different metrics. But when we move on, in this setting, diff pool should be the second most reproducible model because it has 2 different first rank and 3 different second rank. And then when we sort all of these models by majority voting, we see that GET is the most reproducible model, diff pool is the second, GSN is the third, and so on. However, when we see here, GET model, okay, they found GET is the most reproducible model, but their second best model is SEG. However, here SEG was the 5th. The GCN should be the 3rd one. However, it is the 4th. So the main problem here, how can we trust this model if they measure reproducibility as the best one? However, the rest of the sorting don't match. So it gives us some insights that some of the things are missing here. And one other experimental issues, when they find out the most reproducible model, they extract their model features, and when we see their feature results, what they do, they average all weights from different training setups. As you know, there are different hyperparameters, different views, different data sets that they train a specific model. So they take all of the features from each of these settings and they average all weights from different training setups in an element-wise manner. And here, for each of the specific features, we see the decision-making importance of each of these models. This averaging process can significantly alter biomarker importance. The scores of biomarker importance are quite close to each other. Here, for example, they find that posterior cingulate cortex is the most reproducible feature, and they found some articles about the importance of it. However, as I said, since they averaging those biomarkers and the scores are really close to each other without any significant statistical significance, we cannot be sure if those features are really the features that help a specific gene in its decision-making process. So these are we'll define problem statement here. We represented our data sets as here, shown here. The set of brain connectivity multigraphs is denoted as G. Here, each of the multigraph data belongs to a specific patient, and each of these graphs we can represent them as an adjacency tensor, and it's a 3-dimensional tensor n sub r times nv. Here it is basically we divide. We'll just get to that. We divide the brain into a 35 different regions and are represented, and NV comes from N view, how number of views that we have in our data sets. In this case, 6. We construct data sets for each view. As shown here, it's a fault and the specific view that this data set belongs to. And the goal is to assess and rank a set of GNN models. We will sort GNN models and we'll assign a score to each of these one. And we'll try to determine their reproducibility capability. The goal, as I just said, is to assess and rank a set of GNN models based on their reproducibility capability. We define reproducibility capability as GNN models having the same weights under different training setups and data distributions. However, in this thesis, we take account reproducing the last layer in order to simplify the problem and compare it with the previous work. However, and in addition, we assume that reproducing the last layer will tune the other layers to some extent because they are interconnected to each other. The objective of the models we'll assess for reproducibility is to classify 2 different brain states. If this person is autism spectrum disorder or it's a normal control. After training the models for classification, we measure their reproducibility using their weights. We'll measure interview and intermodal reproducibility, as I said, as a fair comparison with RG select. So here, we basically define R is to represent the biomarker vector of a specific GNN model. Using different data sets, those are some faults that belong to the same view and different views. We have, say, 5 different cross-validation and 6 different views. We have 30 different data sets, and we have 5 different models. We train each of the architectures with each of the models, and then we take their last layer to represent using R. And then we define W such that it's the absolute value of the vector R. We need absolute value because we care about the magnitude, how much they contribute of a biomarker. And then we determine the min and max values across all of these features. We have 30 different data sets, 5 different GNN models, and 35 features in each of the models. We go and get min and max values, and we define a new vector n, so that we can normalize each vector using a min-max normalization. In this way, we can know how big each biomarker in different configs contributes to a decision-making process. To assess the significance of individual biomarkers, we insert all biomarkers into a matrix for a specific view. For example, we have 5 different cross-validation. For a specific view, we'll have 5 different scores here. To assess the contribution of individual biomarkers, instead of averaging some things, we establish a row-based function f, and it basically takes L2 norm of the matrix in a element row manner. We then introduce the vector J by selecting the top R biomarkers from L vector. We also introduce T, which signifies the indices of these top biomarkers. Indices correspond to biomarker names, and we'll use this for intermodal scores. Here in this schema, we are talking about interview reproducibility, and then we establish a distance vector D that also takes L2 norm of each of the combination of the vector j. The vectors j represents each view, and we just trying to see the difference, how they are far away from each other. Because if they are close to each other, the distance will be close to zero, and it means it will perfect reproducibility. That's why we call this D a distance vector. And as I just said, this distance vector is a measure of how far the biomarkers obtained from different data sets are from complete reproducibility. Sorry. And then finally, this distance of this vector from zero gives us the score. So instead of averaging matrices, in order to reduce all this information into a one specific number, we use continuous space and using L2 norm in order, and we model this reproducibility as a distance problem, and then we have a specific number about reproducibility of a model. Here is the general schema of our pipeline. We just train all of these models with different training data sets. We extract their weights and normalize them. And then we put all of these features in a element-wise, in a biomarker-wise manner. And then we just want to understand how much each of the features contributes to the decision-making process. In order to do so, we use L2 norms for each biomarkers in each view, and then we take their vectors, and for each specific view, we combine all of these vectors, view vectors, and check their distances from the 0 point in order to see how much of the views are close to each other for a perfect reproducibility. Because for a specific problem, no matter what view we have, we think we'll have some common characteristic independent of the views. And then once we have the distance vectors, we just like to see how much it is far away from the zero vector, so that we can see the reproducibility of our model. If this number is close to zero, it means a good reproducibility, or if it goes to infinity, it doesn't have any good reproducibility. For intermodal reproducibility score, we had introduced J vector by selecting the top R biomarkers from L vector. And as we just said, we now introduce T, which signifies the indices of these top biomarkers. For each GNN model, the index vectors are average, element-wise to form T. And subsequently, just as in the RG select one, we created a GNN to GNN matrix. We represent each of its slots shared between first GNN models, two GNN models, and summing this matrix along an axis yields a lot of intermodal reproducibility score. We don't think this will give us some good results, but we do it for a RG-select comparison and check our hypotheses and see that our hypothesis selections are correct, in order to see that this intermodal reproducibility score does not give us good results. We do it for that. We'll compare RepNet and RG-select. We first give a little bit detail about data sets, and then we cover interview reproducibility scores internally. Are the GNN rankings consistent across different training settings? If a model is reproducible, it means that no matter what hyperparameters that we use in our different training configurations, we'll have a model, we'll have an architecture that is in the first place in terms of reproducibility. If our method can show this better than RG-select, we can say that our model is much more consistent compared to the RG-select. Next, we touch upon intermodal reproducibility scores, and we finally introduce an external validation to compare two methods. Using a basic and interpretable model other than these methods, even if we show that RepNet is consistent across different hyperparameters, we need to compare it with RG-select using a common method. We'll just show that RepNet is much more consistent, but when we do that, we are checking RepNet inside and RG-select inside. However, we also need another method that we apply both RepNet and RG-select and shows that RG-select is much better than RepNet is much better than RG-select. We also need that for a rigorous and solid experiments. We have a data set for autism data set. 150 patients with autism, 150 and normal controls. We have left and right cerebral hemisphere, and as I said, divided into 35 cortical regions, and 6 cortical measures, in other words, views, are utilized, and those are the names of it. So, for interview score, a higher score in RG-select implies better reproducibility capability. However, a lower score in RepNet implies better reproducibility because it is the distance from the complete reproducibility. This is what we measure in RepNet. So since they are different than each other, we compare two methods based on how they rank the GNN models. Those are the results. But it is much more clearer here. Here we see GNN models were ranked based on their reproducibility scores. For example, here we have right hemisphere data set with top 15 features. We take 15 features, top 15 features, and apply L2 norm to these 15 features. 10 features, 5 features, and so on. And we also do that for left hemisphere datasets. And we see that RepNet demonstrated a more stable and uniform ranking of GNNs compared to RG-select. Here we see SEG model is the last one. Gets are same in the same data sets. Okay, it's not perfect, but we can get the consistency in the data sets of right hemisphere and light hemisphere. And also here, other than this one, which is their this is right hemisphere T5, the numbers, the scores are really close to each other. We see much more uniform and stable. Or we can see RG-select, all the colors are mixed. Here, green represents GCN, yellow represents diff-pool, and we see the uniform here. The successful internal validation of RepNet has been demonstrated through this experiment, actually. And in terms of intermodal reproducibility score, we had explained that we separated interview and intermodal reproducibility. However, on the RG-select, they use both of these to generate one specific score. So no matter interview or intermodal, they get one score. So no matter if it's intermodal or interview, they use the same scores. And another one, we mapped scores here between 0 and 1. However, there's no specific range in RG-select, and it is possible to see negative values as it uses the Pearson coefficient. They use this. So because of the method itself for intermodal scores, the higher value means better reproducibility capability in RepNet. This is different than interview reproducibility also in RepNet. In a classification problem, achieving a high score in the specified metric signs a successful model. However, the reliability of the relevant metric is a meta problem. And methods like RG-select, RepNet are in pursuit of solving this problem. There is no direct way we can measure how successful our method is because we are proposing a method that measures a metric. We are not trying to optimize a metric. Previously, we demonstrated that our method outperforms in terms of internal consistency. However, we also need to demonstrate that it outperforms with an external method. If a method serving the same purpose contains parallel elements, parallel keys to the ranking done by RepNet compared to RG-select, we would have tested RepNet with an external validation. So for that, we organize biomarker ranks obtained from different trainings and computed interquartile ranges. In this way, we map each biomarkers to its rank of importance within all biomarkers. The set key to the power I sub m indicates the ranks of the values of the ith biomarker from all training instances. The IQR operation, interquartile range, is then applied to each of these sets for each biomarker in a model. We obtain a list when we compile them into a list, we obtain the set that consists of the values which represent each biomarker's overall consistency. So we basically see that for a specific feature, say the fifth feature is the second most important feature. We take all of these, put them into a list, and then checks the interquartile range. In this way, if a specific feature, no matter what different training configuration it is in, will have this same or nearly the same ranking of importance. And when we do that, that feature's interquartile range will be close to 0. And if we extend it into all of the features for a specific model, the better reproducible model, we see its features interquartile ranges are close to 0, meaning to a better reproducibility. This is different than the two methods, RepNet and RG-select. And the parallel elements and keys in this method, if those key elements are parallel to the RepNet, we'll have an external validation that RepNet outperforms RG-select. And here, we see that GCN models are IQR range values for each of the specific values are close to 0, and then comes diff pool, and then there's a huge gap between these two models and the three models, and then we see here these findings. In our discussions, two different topics we'll discuss: investigating interview reproducibility score, external validation results comparison, investigating intermodal reproducibility, most reproducible biomarkers, and their clinical reliability. As we said, GCN is the first, diff pool is the second one, SEG is the lowest. The other two models are, they're split into two equal chunks here, seeming like a fluctuation. And IQR-based experiment, as we just explained in the previous slides, here we can also see that GCN has the best, diff pool has the second best. And GCN and diff pool have way better reproducibility. And SEG does not emerge as having worse reproducibility, does not count towards RG-select's though. And here we can see that GCN is the best reproducible model, whereas diff pool is the second. Okay, we have SEG here as the worst model. Here we cannot really say that, but it doesn't count a negative impact on RepNet because it doesn't count any positive impact on RepNet also, RG-select also, because RG-select does not have anything to say about SEG also. So for intermodal reproducibility scores, as we said, they focus on how well GNNs captures common biomarkers across different models. It hypothesizes that different models learn similar biomarkers for a given problem. A good model has more intersection with other models. Here, at least for a specific RH dataset, GCN has the most intermodal reproducibility score. Here, they are in bold. However, it doesn't detect any pattern in left hemisphere datasets. And no patterns are found for diff pool either. So we can basically say models with poor reproducibility prioritize biomarkers that do not overlap with those of the models with high reproducibility. This hypothesis were not good. So we couldn't get any insights from it. And these results show that. And the final part on discussion, we had already covered internal and external consistency of our methodology. Finally, we will evaluate our method by checking its top biomarkers, whether they are clinically relevant or not. So to do so, we extract all biomarkers from the last layer, independent of the data sets, the top number biomarkers. And so we use GCN and extract all of the biomarkers from each of the training configurations. And we apply L2 operation biomarker-wise and obtain an importance score for each biomarker. Using these scores, top 3 biomarkers we selected, precuneus cortex, bank of the superior temporal sulcus, and lateral frontal cortex. And we find some good and critic papers that tell us about these biomarkers' relevance with autism spectrum disorder. So, what assumption should the superior method rely on? We eliminated the intersection among various GNNs shared biomarkers. And our top biomarkers were clinically meaningful. How we sort GNN architectures and what were the highlighted keys? We saw that GNN architecture exhibits the best interview reproducibility capability, whereas the diff pool does the second. And SEC emerges as the model with the lowest reproducibility capability. And GCN and diff pool notably differ from the rest. GCN seems also the most reproducible model in terms of intermodal reproducibility-ish, because this is not as distinct as for interview reproducibility. Besides, relying on this may be inaccurate due to its underlying assumptions, as we just discussed. And the final question, are the reproducibility scores correlated with their capability? RepNet score for GNN architectures almost aligns seamlessly with the outcomes from our external validation, confirming the reliability of our approach. So we basically, in this study, first review the literature and gives the state of the art, and then we criticize it in 3 different areas: assumptions, its theoretical foundation, and experimental design. And we address the concerns in RG Select. And the address concerns in RepNet, they eliminated assumption of biomarker similarity across different architectures and used L2 norm rather than averaging operation for information reduction and preventing the information loss. For experimental design, we use 3-stage approach for a robust and rigorous experimental design. It's an internal validation, external validation, and clinical relevance. We use internal validation to see our method's consistency. We use external validation for the independence of our method and clinical relevance for medical issues. As outcomes, we identified most reproducible model with a more rigorous and precise method. We extract crucial biomarkers and examine their relevance. And we affirm the selection of new assumptions. We see them, they are working. It validates the method with a robust theoretical foundation. And we ensures the integrity of experiments using 3-stage experiments. For future works, the issue of the overlapping state between GET and GUnit misses for complete consistency. We could get the consistency inside of each of the data sets, right hemisphere and left hemisphere, but we could get a complete consistency as in SEC, GCN, and diff pool. And also investigating the explainability of why GCN and diff pool have good reproducibility capabilities compared to the other models. We measured GCN and diff pool, but we really, but why they are good reproducible model? We focused here on reproducibility, not in interpretability, at least in a direct way. Also investigating it and taking it further in a next step was the out of this work scope. This also may be another step for future work. I took a bit of much of your time. Thank you for your patience. That's it.
Okay, thank you, Hızır. So since Hakan has a meeting, so I give Hakan priority to ask his questions. Go ahead, Hakan.
Teşekkür ediyorum sunumun için Hızır. Bir tabloda bazı minus değerler gördüm. Onlar neydi? Söyledin mi? Emin olamadım aslında ama.
Evet, saniye hocam hemen.
Burada gördüm.
Hocam şöyle.
Sıfırla bir arasında, özür dilerim. Sıfırla bir arasında bunları biriktirdik gibi bir şey de söylediğini ya da